Hello, my name is Parminder Kaur and I am doing ME from Thapa University, Patiala. My thesis topic is plant disease recognition using fractional order Zernike moments and SVM classifier. As we all know that Indian economy highly depends upon the agricultural productivity, so it is important to protect agriculture and plants from various diseases. Plants mainly suffer from diseases which are caused by malignant viruses, bacteria and fungus, and if proper medication is not provided at proper time, then quantity, quality and productivity will be affected. Here we are presenting the plant disease detection using moments. Moments are specific quantitative measure of the shape of a set of points. For example, total intensity, centroid, information about images, image orientation, etc. Moments are of various types, but here we are using orthogonal moments. Orthogonal means statistically independent or mutually perpendicular. These are the important characteristics of the orthogonal moments. The kernel function of the orthogonal moments is derived from the orthogonal basis set. They require less computational precision to represent images comparative to other methods of image representation. They are rotation, scaling and orientation invariant and shows very less information redundancy due to orthogonality. Orthogonal moments can be continuous as well as discrete. This is the broad classification of orthogonal moments. Before orthogonal moments, there were complex moments, rotational moments and geometric moments. These double-sided arrows mean that each of these moments can be expressed within the other formulation, while single arrows denote a subclass relation. So the continuous moments include legendary moments, Zernike moments, generalized pseudo-Zernike moments which gives birth to pseudo-Zernike moments, Chebyshev-Fourier moments. And the discrete moments include Chebyshev moments, Kirchhoff moments, Raka moments and Dewey-Hahn moments. Here we are presenting the fractional order Zernike moments. So this is a short description of Zernike moments. Zernike moments are a set of complex Zernike polynomials which were introduced by an optical physicist named Fritz Zernike. They are defined inside a unit circle over polar coordinate space in the interval 0 to 1. This image shows the first 21 Zernike polynomials. Here n represents order of moments and m is repetition. Both are having value equal to 5 here. The moments at each value of n are orthogonal to each other. Like at n is equal to 1, it can be easily seen that both the moments are mutually perpendicular or orthogonal, which increase in with increase in the value of n, it will become difficult to see the orthogonality due to increase in dimensionality. This is the literature survey. Here, first of all, Dr. Liu has presented a general form of Kirchhoff transform, which is known as fractional Kirchhoff transform, with the use of eigenvalues and eigenvector decomposition scheme. And the fractional orders are adjusted for fractional Kirchhoff transform robustness and watermarking performance. Another approach introduced by Dr. Bin, which includes the fractional order orthogonal moments represented in Cartesian polar coordinates through shifted legendary polynomials. It has been shown in this study that fractional order moments perform better for face recognition, image reconstruction and region of interest feature extraction. Another author, Abraham, has introduced a new technique for disease identification in Ethiopian coffee plant. The Diseases which affects this plant are leaf rust, berry disease and wilt disease. Then the comparative analysis of 4 classifiers such as artificial neural network, naive Bayes, k-nearest neighbor and a hybrid of radial basis function and self-organizing map is shown. And also the 5 different segmentation techniques are used, which are as FCM, k-means, Gaussian distribution, OTSU and the combination of k-means and Gaussian distribution. The comparison is also presented here. And another author which has used the convolutional neural network for plant disease identification, he has used healthy leaves and 13 diseases of different plants which affects different plants. The images taken for implementation are healthy leaf images, background images, and the images having diseased leaves of pear, peach, apple, pear and grapevine. So here our objective is to recognize that whether a plant leaf is healthy or affected by a disease, and if it is affected by a disease then the disease will be recognized. And here the fractional order Zernike moments are introduced for feature extraction from leaf image. This is a block diagram for the leaf recognition process. In the training phase, the whole plant leaf image database is in the RGB format. So each image from the database will be firstly be pre-processed, which includes the image resization and conversion to grayscale and the image normalization. After that the image will be ready for feature extraction, and then the fractional order Zernike moments are extracted from each image, which generates feature vector corresponding to each image, and all the feature vectors combine to form a feature matrix. Then the feature selection will be done on that feature matrix with the use of random forest. After that, after selecting the features, the data will be converted to training and testing data in the 70-30 ratio. The 70% data will be used for training, which is put into the SVM classifier for its training. Now then in the testing phase, if an image come for recognition, then that image will firstly be pre-processed, and then the same process of feature extraction and feature selection will be repeated as previous. Then that feature vector is put into the SVM classifier, which will which will recognize the disease and label it. Now there are two types of square to circle mapping techniques. One is inner circle mapping and the other is outer circle mapping. Figure A shows the inner circle mapping and figure B shows the outer circle mapping here. In inner circle mapping, the center of the image is converted to the center of the unit disk, and all the pixel coordinates are normalized to the normalized to unit disk. Here we can see that the corners or edges of the image are not included in the unit disk, so there is information loss in this approach because the corner edges are not included in the moment calculation. However, in the outer mapping approach, whole of the image is mapped inside the unit disk, so there is no information loss. Due to this, we have used here outer circle mapping technique in the moment calculation. So firstly, fractional order Zernike polynomials. The definition is almost similar to Zernike polynomials. The difference is that Zernike polynomials consist of integer order. However, the fractional order Zernike polynomials consists of fractional order. The fractional order Zernike polynomials are a set of orthogonal polynomials that are defined inside unit circle, where a, p, q, r, theta represent the fractional order Zernike polynomials, and b p q r comma theta is the other radial polynomial. So fractional order Zernike polynomials are a set of orthogonal polynomials that are defined inside a unit circle. Here a p q r comma theta represent the fractional order Zernike polynomials, and b p q alpha comma r is the radial polynomial. Here p can be 0 or a positive integer such that p should be greater than or equal to 0, and q can be positive or negative integer satisfying the constraints. Mod of q lies between 0 to p, and p minus mod q should be even, and I is root minus 1, and r represents the length of vector from origin to pixel x comma y. The angle theta represents the angle between r vector and x-axis in the counterclockwise direction, which is given as tan inverse of y by x. This is the formula for calculating the radial fractional order Zernike polynomial, and the second formula is for radial Zernike polynomials. Here we can see the difference that in the radial fractional order Zernike polynomials there is addition of a variable alpha. Alpha is belongs to real line, which change the integer order to fractional order. So that's why the order is q plus p for radial Zernike polynomials. However, for fractional order Zernike polynomials it is q plus alpha p plus alpha minus 2 by 2. This is a graph between r values and the radial fractional order Zernike polynomial. This graph is drawn to check the numerical stability of the polynomial and to find the value of alpha at which more efficient results can be obtained. Here on x-axis there is r, and on y-axis represent b p q alpha comma r. Here we can see that when r tends to 0, the value of the polynomial is extending to infinity, which represents the numerical instability of the polynomial. It will not represent the image. It will not represent the image features accurately, and so we'll draw the same graph at different value of alpha. Here at alpha is equal to 1, we can see that the values of the polynomial are approaching towards 0. Like in this, it is contracting. At alpha is equal to 2, it has the value of the polynomial is approaching to 0, and and at this graph at alpha is equal to 2.5, we can see that the graph has almost is approaching to 0, and it can be seen, and the values are not extending to infinity now. So it will provide this value will provide more accurate features or moments of the image. So with the increase of alpha value, we can obtain good accurate moments, and the condition will come where the stagnation, and after the stagnation point will come at which with increase in value of alpha there will be no change. So this is fractional order Zernike moments. These are extracted from image by projecting it onto complex orthogonal fractional Zernike polynomials, and for an image function I r comma theta, they are defined as this equation 4 and 5, which is p plus q and integral 0 to 2 pi integral 0 to 1 I r q theta r theta, and a PQ r comma theta is the radial polynomial, and with r dr d theta. These are the different because we are using here grape leaves specifically for recognition of diseases. So there are three main diseases present in grape leaves, that are black rot, esca, and leaf blight. So we are here recognizing the leaf to be healthy, black rot, esca, and of leaf blight. This is the sample database in which the first row represents the healthy leaves, and the second row is black rot, third row is esca, and the fourth row represents the leaf blight leaves. So this is a pre-processing step in which firstly we have the original image, which is resized to 50 cross 50 pixels, and then that image is converted to grayscale image. So these are the results obtained after experimentation. We have done experimentation at order 20 and order 30, and with or without feature selection. Also we have calculated fractional order Zernike moments at different values of alpha and compared it to Zernike moments. So it can be seen here that we have achieved the maximum accuracy of 95.12% using fractional order Zernike moments at alpha is equal to 2.5 and at order 30 with feature selection. This is the visual representation of the previous table, which is shown in the form of a bar graph. So our contribution to society is introduction to fractional order Zernike moments that can capture more feature details compared to integer order Zernike moments and other methods, and the application of continuous orthogonal moments to plant disease detection is proposed, and to automate the detection of plant leaf diseases without the need of an expert, which is more efficient and faster framework to recognize diseases. So in the end, we conclude that the new version of continuous orthogonal Zernike moments is introduced, and which is known as fractional order Zernike moments, and FZM used to extract features, and SVM classifier is used for the plant disease detection, and we have seen that FZM provides more promising results compared to Zernike moments at all values of alpha, and however we have achieved the highest recognition rate of 95.12% using fractional order Zernike moments at order 30 with feature selection, and at alpha is equal to 2.5. So the future extension of this work could be to analyze the proposed approach for image reconstruction, character or face recognition, and iris identification and image watermarking. The other classifiers that can be incorporated here are artificial neural network, k-nearest neighbor, decision tree, and random forest. Also other continuous and discrete orthogonal moments can be made fractional and applied in image processing area. So these are my publications, and these are the references. Thank you.